All right, and so now after we have seen thoroughly how to carry out the computations for all the approximation methods we have learned here in real detail steps, then now let's talk about the error bounds. So the errors that's created by any of these approximation answer with the actual answer. So here I'm looking at error bounds. And I will explain more precisely what error bounds mean. But so now I have, as I was going through the examples showing the computation steps for how to get these approximation methods done right here, and I already put into your awareness the following things. So let me once again swing back to the other board. And so with this famous problem, that definite integral that we were looking for, the numerical answer to that. So this is the exact answer that somehow the computer was programmed to get that value. And we already used, throughout example 1, we already calculated T4. So the trapezoid, using the trapezoid method with 4 trapezoids inside of our subinterval, inside of our interval from 0 to 1, we came to having T4 equal 1.475 17871 435. Okay, and it could be a lot longer. Okay, and then we came down to T6 using a trapezoid method again with six trapezoids here, and so we came to that answer 1.4637107, okay, 6045, and I have to constantly keep looking back at my whatever the reports of the answer we've had on that stored on my computer screens over there. So and back to what I was saying earlier, I already put into your awareness that none of these answers is the real answer to that actual definite integral. So any of these answers we found was only used as an approximate to the real answer here. So in other words, if we compare T4 with the real answer being written here, there's a slight difference, and that slight difference there's a slight amount of error. Okay, so that slight difference, that's what I'm talking about. It's the error. Okay, so if we're subtracting, see, so the error in this problem right here, if we went with T4 immediately, we have an amount of error that's an amount of error here. So I notate by a capital letter E, that's for error. Okay, so all we do is simply subtracting our actual T4, right, with the actual integral value I right there. So I here, this is believed to be the exact value. Now let's for now trust whatever the computer is having for us, and that actual value that numerical value even goes a lot further than just those decimal displayed here. Okay, but so error is always produced by taking our approximate value, subtract the real answers. So errors can be, so in this way, error can be positive or negative depending on whether our answer is above the actual answer, slightly above the actual answer, or our answer for an approximation could be a little bit below. But so in any case, the amount of error produced here, so in this case right here, now we got closer, okay, and so it was closer within 2 decimals. But in the end, it's starting to be off after, starting at the 3rd decimal and so on. And so again, we're seeing some error. So the amount of error here, but for sure the amount of error here is going to start being less and less error. So as we go, so in any way, so as we go into more subintervals, right, then we're going to have less and less error. Okay, but so here the error is done by subtracting the actual answer from our approximation value right there, and or somebody else can do that the other way. But so in my way of how I'm writing the calculation of the error, then a positive error means again the approximation is slightly above the real value, or if it's a negative, then it's going to be, it means the approximated value is slightly below the actual value. Okay, and so same way, I also went through using the Simpsons method with 4 subintervals, and the answer I've had there was, as I recall, 1.46 37107 and something a lot longer. And I actually just now realized, but it shouldn't really matter, but I actually realized I wrote down the wrong approximated value for this T6 right here. So the T6 here this is supposedly T6 right here. So let me correct that. 1.475 178 71435. So that's the answer we've had for T6. And then T4 was 1.4906. Okay, 788617 and a lot longer. And then we came down to, so SS4 was this value right here. Okay. And 6045 and a lot longer. So that's the value we had for SS4, and then SS6 for here came out to be 1.462. Okay, and 87345 All right, so these are all the values that came out from our previous work. And so now when you can see that, so when we turn our focus over to the Simpsons methods right here, then of course, again, rule of thumb, the more subintervals we have, the better answer, the better approximates we're going to get, and better in the sense that here I'm looking at less error, because so here 1.463, this answer that came out from the Simpsons methods with 4 subintervals already came close within 2 decimals. Okay, and so let me correct what I said earlier about the trapezoid, but for the trapezoid we were only correct up to within 1 decimal. Yeah. Okay, but now using in example 2, using the Simpsons rule, and it happened in this problem for this integral over here, but other problem it may be, trapezoid can be better in terms of the accuracy. Okay, so don't make a judge just simply because in this particular integral we had the Simpsons method to seem to arrive at the closer approximate faster. Okay, but now for Simpsons method with 6 subintervals, we came to as close as within 3 decimal places for accuracy. But in the end, any of these amount of error, okay, any of these amount of being off right there, they're all, so for Simpsons method with 4 subintervals, we're going to go SS4 minus the actual answer. That's how we can determine the amount of error. And then SS6, okay, Simpsons method with 6 intervals, and subtract the actual value of the integral. That's the error. Okay, but again, any of these errors, either you are going with the trapezoid method or the Simpsons method right here, they're all going to produce it could be positive, it could be negative. It all depends on how where your current approximated value is compared to the actual value. Okay, so now I'm talking about, in this problem right here, mainly I'm talking about the error bounds. So what does that mean by an error bound? An error bound just basically means, so the amount of errors we produce right there, there's a certain limit of how high or how big that error amount can be produced, or how low that error amount can be produced. That's what it means by error bounds right there. Okay, so now generally speaking, at least in this video lecture, I skipped going through the computational steps for the midpoint rule, but the midpoint rule is still being part of this particular lecture right there. The reason I skipped the computational step for midpoint rules in the approximation work, because we already went over that in earlier video lessons when we were still doing the Riemann sums. Okay, but now as when we're talking about error bounds in general, then so as a generality here, I'm going to define a capital letter E with a subscript M. Okay, and many textbooks are doing the similar thing right here. So the error produced by the lowercase letter m, okay, that's the error amount, is generally defined as, so, and the lowercase m right here is for midpoint. So if we were doing the midpoint as the approximation, then the error produced by doing midpoint approximation will be midpoint rule with some general n number of subintervals minus the actual interval, actual value, numerical value of your integral problem. So that's the error produced by midpoint rule. That's what the capital letter M is for. And then if we were using trapezoid rule, then ET, okay, error is famously notated by capital letter E. But down the subscript T here is indicating that this is the error that's produced by doing the trapezoid approximation method. And so, but similarly, that means we run through the trapezoid methods with any general and subintervals, and then we subtract that approximated answer. We subtract the actual answer from that approximated value right there, and that's how we produce the amount of error for using the trapezoid method. And so similarly, now we can have also an ES, okay, the error produced by the Simpsons method, okay. And so Simpsons method here is going to be T, and actually this is not T, this is SS, okay, the amount of, the approximation using Simpsons method with n subintervals in general minus I right there. Okay, and these are the three fundamentals about how we define the amount of errors produced by running any one of these approximation methods. Okay, but still that did not explain about the error bounds. So now once you are well aware what errors is, right, the errors in any of these, the error produced by any of these methods here, just simply the difference between the value of the approximated value that came out from the methods and subtract the actual final answer, the actual answer that a lot of times we don't know, and that's why we use approximation. Okay, but so now once we have that idea in mind, and each of these error can be positive or can be negative. Okay, that's one thing you gotta keep it in mind for me. So now an error bound, as I spoke earlier, error bound is sort of like a limit, an upper limit and a lower limit, where each of these amount of error can be possibly in between. Okay. And so now it is proven. These are actually theorems, but now in these days they are introduced throughout textbooks as just a rule, a law to understand, like that, okay? And no one in these days remember who came up with these error bounds anymore, okay? So sadly I can't introduce who that was to be credited to. But now it's proven that the amount of error produced by the midpoint rule at generally any number of subintervals, if we put that in absolute value, okay, then that will be, so this amount of error in absolute value will be less than, generally is proven to be less than or equal a constant k. And be patient with me, I will explain what that constant k is. A constant k multiplied with b minus a, and so b here is the upper limit of our integral problem, and this is the lower limit of our integral problem. Raise to the third power on that difference is b minus a, and we divide by 24 and square. So this is a formula that points out the error bounds for any errors produced by the midpoint rule right here. Okay, and then so n here is n is the number of subintervals. Okay, and k is the value that satisfies. K must be a constant that satisfies. So it's a constant, but it satisfies f double prime, the second derivative of your current function, in absolute value less than or equals k. So k here is a constant that satisfied at any x value your function, your f double prime in absolute value must be less than or equal to k. Okay, and so when we actually get into some problem, I will show you how we can recognize that k right there. Okay, so that's what the meaning of the k value. So now once we recognize k as a constant that satisfies this requirement about your function f of x, then the error that's produced by the midpoint rule in absolute value will be for sure less than or equal this expression. Okay, so that's the error bound for midpoint rule over here. I am going to swing over to the other board to write down the error bound for the Simpsons rule, and actually the trapezoid rule first. All right, and so now as far as the error bounds for the trapezoid rule, so ET in absolute value, the amount of error produced by the trapezoid method in absolute value is known, is proven to be less than or equal k times the difference b minus a raised to the third power divided by 12 n squared. Okay, so now once we had a clear understanding, once we've already had a clear understanding of what that k was from the error bound formula of the error produced by midpoint rule, then this k right here, that same k is proven to be also part of the error bound formula for the amount of error produced by a trapezoid method. So this k and the other k is the same k, and again, n here is the number of subintervals in your the subintervals in between that interval that you're integrating over. Okay, so n is the number of subintervals, just like that, number of subintervals. And then k has to be a value that satisfies, okay, k satisfies the function double derivative or second derivative of the function in absolute value less than or equal k. That's what we know. So one same requirement about the k right here, then we can really, it's useful for two error bound formula. Okay, and so one same explanation of all these of the n and the k right here. So I can actually put the other formula on this little empty space here as well. So the error bound, the error amount produced by trapezoid method in absolute value is also less than equal to k. Okay, the same k here times b minus a to the third power, but only divided by 12 n squared. Okay, so we got a formula for that, and we had a formula for the midpoint rule. Okay, and so now let's get to an actual example right there where I will have a chance to explain exactly what this does for us. Okay, what any one of these does for us. Okay. All right, so now I am going to produce example 3. Okay, let's say for example 3, even though I'm still using that same definite integral that we have been using throughout the previous two examples, but I want anyone viewing this example as pretend that you are seeing this integral as a brand new integral, that you have completely no idea what that final answer is. So pretend that you don't know the final answer for this. You only know that this integral will have a final answer, an exact final answer, but we just don't know what that is. So that final answer is called I. Okay, the answer to this definite integral. So once we're given with that, now the question is being raised as following: how large? Okay, so with that integral right here, and of course we cannot use any fundamental technique right here to find that answer. We cannot go through the fundamental theorem of calculus. That's why we're gonna break it down to subintervals. The question now is that how many subintervals, or how large should n be? Or in other words of saying, how many subintervals should we use? How large should n be to ensure? Okay, to ensure. So how about to ensure EM? Okay, the amount of errors produced by the midpoint rule. That's what the M is. To ensure EM is, so my important word here, and start catching with the way how it's worded out there. The amount produced, the error amount produced by midpoint rule is being within 0.0001. Okay, within 0.0001. Okay, so what does that mean by being within 0.0001? Okay, so here's how it is. Here's what it means right here. Now, here you can notice in the beginning I write this down without the absolute value sign, but my formula that I introduced has absolute value signs. Okay, so let's hold on to that. Here's the E itself means the error amount, and being within 0.001. So that means, okay, and again, EM, the error amount produced by the midpoint rule is always the midpoint rule at any number of subintervals minus I. So that's right out from the box. That's what EM is. That's what the error amount produced by the midpoint rule. Okay, the difference between the approximation value, the approximated value, and the actual answer of this. And again, I'm asking anybody to pretend from scratch that we don't know the actual value here. Okay, so being within 0.001 right here means, and being within 0.001 of the actual answer. So in other words, it means the actual. It really means this approximate is anywhere up and down. Okay, anywhere. So from the real answer, it's anywhere up and down by 0.001. That's what it means by the error is being within 0.001. Okay. The midpoint rule approximation is anywhere anywhere 0.01 above or within that, or 0.01 below the actual answer. That's what the plus and minus is. Okay, and so now to be precise, and using the equal sign here is not exactly, it's not the precise way, but a more precise way of saying that is that this margin of error has to be anywhere less than the actual answer plus 0.0001, and then being more than the actual answer minus 0.0001. That's how precisely we can write that as a triple-sided inequality, as a three-sided inequality. Okay? And so in that way right there, now I can subtract, and only for this part A, then I have to give a lot of explanation for you to see the logical details of that. And once we've got an idea of that, the later problem will be a lot faster. So that means from this three-sided inequality, this midpoint approximation with n subinterval subtract the actual answer has to be anywhere greater than or equal to minus 0.0001 and less than 0.0001 right there. So this difference here, we want that to be anywhere, so the actual difference now is to be anywhere greater than minus 0.001 and then less than 0.001 positive. 0.001 positive. Okay, so it's in this boundary there. So we want the error. So if we now recognize this is this part right here is our EM. So in other words, now I can see that what we want here is that the margin of error, the amount of error produced by the midpoint rule, that has to be inside of that interval. Okay, so that's what within means. So we want, so now I have to really note this, that this is what we want. We want the approximation method, the error produced by the midpoint rule to be anywhere within 0.001. That's what this ultimate value is. But now, hey, algebraically, seeing this current inequality right here, and after so much explanations, now this final inequality is the same as, so in other words, what we want here, we want the error produced by the midpoint rule to be within 0.001. So that means absolute value of m has to be less than 0.001 right from that. So this is algebraically right from that earlier three-sided inequality. We want EM in absolute value being less than 0.001. Okay, so this is what we want. And now, in the meanwhile, it was already proven on the other board that EM in absolute value can be less than or equal. But here, this is EM in absolute value can be equal up to this value. Okay, and so here's how I'm seeing it. Back in the problem itself, That means in this way you have to understand. Here what we want is EM in absolute value is strictly falling below 0.0001. But then on the other hand, now I repeat, EM in absolute value is proven to be less than or equal. This or equal right here is important. Or equals the K value. We haven't found the K yet. But here it's B minus A cubed over 24n squared. Okay, so that means strictly we can imply the following. We can imply that based on the two, so we want this, but then this is what we also know. Okay, so together with the two facts that it implies that the amount K times the B minus A cubed right there in expression over 24n squared. This expression has to also be strictly less than 0.0001. Because think about that. Now, both of these inequalities compare directly with EM in absolute value. And so, but in this one here, EM in absolute value is allowed it to be equal up to this, whatever this expression comes out to be. But here the EM can only be strictly less than. So that means logically, you can always pause the video and think about that logic. But logically speaking, if we combine these two as one inequality, then that expression here with the K must be anywhere strictly less than 0.0001. Okay, and so now this is some known fact that we concluded from knowing these two. We want to have this because that's what the question of the statement is asking, and then we know that's part of the problem. Okay, so now I have left this board here long enough, and I wanted to leave it here for a little while to keep switching back and forth to see the formulas, but now I need more space to solve the problem. So let me go ahead and clear out the board here. And we're not doing trapezoid approximation yet, and so let's stay with this formula. Okay, and keep in mind this K here, K is the value that satisfies, K is satisfying absolute value of f double prime being less than or equal to K. So now that's the only fact for us. And by the way, so now I have to remind anyone. So back in this problem, the integral itself here, so what is f of x? F of x is this function. F of x is this function e to the x squared. So e to the x squared is that function f of x right from our integral problem. And that's what this statement is talking about. So we have to get the f double prime of x from our previously recognized f of x from the other board right there. And then from once we've had the f double prime, there will be ways. So at this point there is no one unique way. There are many ways to recognize that K right here. So for this particular problem, allow me to point it out as following. So we knew that f of x is e to the x squared. Okay, and so that means f prime. That implies that f prime has to be, well, because we need f double prime, so f prime has to be 2x times e to the x squared. All right, and so anyone watching this video should be familiar with how I got these answers for f prime. And then that consequently produced further that f double prime, now before putting it in the absolute value, so f double prime has to be, and after taking the derivative, one further derivative right on this function right here, so we arrive at f double prime being, now after all the work and combining like terms and all that, 2 plus 4x squared times e to the x squared. That's my f double prime. So now we got f double prime, but once we've had this, what matters is to recognize the K satisfying this. We're getting closer, but now there are a lot of ways to defend that K right here. The idea is that one generality I want to point out here is when the inequality here says K is the value where where f double prime of x in absolute value less than or equal K means K is the maximum value, okay, the maximum value of f double prime in absolute value of x, regardless of wherever x is. At least in the interval from 0 to 1. How's that? So at least in the interval from 0 to 1, k here is legally thought of as the maximum value of the f double prime in absolute value inside of that interval from 0 to 1. Our integral bounds, okay? And so now taking that understanding in consideration, what I'm about to point out here is not the only way. It's any way it's going to work, right? There are so many different arguments, different ways to argue the problem out there. But now let me show the graph. Allow me to explain that graphically. Okay, so in the graphing space, then this is the graph, at least, and forgive my scaling right here, but okay, this is the graph for f double prime of x right here, because in the end, f double prime or f triple prime, they're all just different functions. And so how I see that now is that f double prime of x, an absolute value sign is just simply making it positive, but the f double prime in the interval from 0 to 1, so 1 is ending at that piece right here. It's not the whole, I'm not taking the entire graph of f double prime of x, but I'm only taking the piece of f double prime of x inside of the interval from 0 to x equals 1. So what it looks like to me here is that we have an increasing graph right here. F double prime of x is an increasing graph. So from calculus 1 understanding, from our understanding in calc 1 in differential calculus, then as long as we can see that a function is increasing or going in one way, just like the way how the graph here looks like, then that means that the right end has to be the right end right here, that right end right there, okay, has to be, and I hope you can see that big enough on the screen, but the right end has to be the maximum, and the left end, so the right end here, I mean the right end of the interval, or when x equals 1, we will reach the maximum on this f double prime. And then on this here, the left end of our interval between from 0 to 1, the left end here is, or must be a minimum value, okay? And so in that way, now I'm ready to tackle it down. And see, you saw that through the graph, and explaining that graphically is not the only way. Somebody else, I mean, if you're a student studying with me right here, then you can always get a hold of me to study about other ways how we can recognize that k as well. Okay, but here it's simple enough, and you all have strong enough technologies in these days in your classroom so that you can quickly get the graph of that. So using the graph to explain is, for me at this moment, is the best right there. And you can see that the graph was already above the x-axis. So having absolute value or without absolute value makes no difference. Okay, and that's the whole. So now what I'm seeing here, maximum of f double prime of x is, see, I have to make that statement, is at x equals 1. Okay, I hope you recall that from the graph that I've had it on the computer screen earlier. Okay, so this is the graph, and only inside the interval from 0 to 1. And in my argument that I made earlier, the graph is increasing at least in that interval that we're graphing it. X equals 0 is here, x equals 1 is here. Okay, so in that way, in a way how it's increasing from the left to the right, then when x equals 1, we will reach the maximum. And so for that, in that way of reasoning, then here's the impact. After we realize about that, then now that's how we recognize k. K has to be f double prime at 1. K has to be f double prime at 1. This is not the same way to recognize k in any other problem. The main generality here is k has to be a value being the maximum of your f double prime inside of the integration interval. Okay, so in this problem, I gave reasoning in a way that I see the graph of this f double prime being an increasing graph inside of that interval. So I made my reasoning that the k has to be that maximum value when we reach x to the x equals 1, the right end point of your interval. Okay, And so now in that way, now feel free to do the calculation. Okay, so anyone following along with this lesson can start doing the calculation independently. We're looking at 2 plus 4 times 1 square, okay, and all that there times e to the 1 square. Okay, so that's essentially e, and then all this here is going to give me a, and that's a 4 plus 2, so it's 6e. That's our k value. So that leads to my k value here, 6e in precise value. Okay. All right, so now that we found a k value, the k that satisfies, and so now needless to say, b is 1, a is 0 in our problem. So now here's allow me to come back to the other board and recall a couple things. So now at this point, once as we are ready to put the pieces together, we want this expression k times the interval b minus, times the difference b minus a to the cube power over 24n squared, all that fancy thing, okay, all that whole expression there, we want that expression to be less than 0.0001. So that means now, and with our k, plus our k is now ready, then we're looking at 6e, okay, because that's our k. B minus a is going to be 1 minus 0 cube divided by 24n squared. We want this expression, but now shockingly, this entire expression now is only dependent on the n variable. We want this expression involving n variable to be strictly less than 0.0001. This is what we carry out from the previous steps on the other board. Okay, and so in that way, here's how I'm seeing it. In the next step, it's just a little bit of algebra. I see that 6e, 6 cancel with 24 a little bit, right? And that gives me, and 1 minus 0 is 1 to the third power, just 1. So we're looking at e divided by 4n squared. And we want this expression, and keep in mind e is another constant, to be less than 0.0001. Okay, and so now that means we can go ahead and solve this inequality here for the value of n that's suitable for our need. Our need here is that the error bounds is the error amount is to be within 0.0001. Okay, we need that, so in that way to satisfy what we need, we got to search for the number of n, how high, how many subintervals do we need, okay, to ensure that amount of error being within that specified amount. Okay, so now solving for n, it's just a matter of solving this inequality algebraically. I am going to take the reciprocal of the inequality on both sides, but be careful when you're working with the reciprocal of an inequality. It's when you take the reciprocal of any inequality, the inequality sign is going to switch direction. Okay, so that's a quick algebraic review right there. So 4n squared over e has to be now greater than 1 over 0.0001. Just 0.0001. Okay, and then so that means in my next step 0.0001. 1 over 0.0001 is the same as. So now I lead to seeing that 4n squared over e has to be greater than. And that gives me 10,000. Okay. All right, and so now we will just continue solving for that. So in this way right here, I'm seeing n squared has to be greater than. I'm going to multiply the e to that 10,000 and divide both sides by 4 like that. So I'm looking at, and 10,000 divided by the 4 is going to give me 2,500, okay, but times e, and e itself is not a very nice looking value right there, but at least now we have come down to n squared got to be greater than 2,500 times e, okay, and so now let me now switch to the other board right there, and now I don't want to erase the first line right here because I want to save that there, but continuing from the last step, then here we can just simply take n, solve for n by taking the square root on both sides. And so it's all positive quantity on both sides, so n has to be greater than the square root of 25 hundredths times e. And now we are ready for a final calculation, a final computation. So let's go ahead and put that product inside the square root and get a final answer here. All right, so now I'm looking at, in this way, n has to be, keep in mind n is the number of subintervals. It has to be whole integer value only. Okay, but we'll get to that. But for now, as far as the calculation, straight out from the calculation, n has to be greater than 82.436 and a lot longer. Okay, 82.436 and a lot longer. But that now means, keep in mind what I just said earlier, n is the number of subintervals. So n needs to be just whole integers. And here we've proven that n has to be above, see, strictly above 82.436. So it doesn't matter how decimal that is, but being above that, that means at the least n has to be 83, then above, 83 or above now. So in that way, I can make the following conclusion. It's all due to the fact that n has to be a whole value, an integer. Okay, so now with all these algebra worked right here, we've come to conclude that in order to ensure this estimate, to ensure this error bound to be within 0.0001 right here, then n has to be greater than or equals. The least here is 83. Okay, and that's what it is. Okay, and so or verbally or in words, n must be, okay, at least 83. Okay, meaning we have to use at least 83 intervals or anywhere more than that, and that will ensure our error amount produced by the midpoint rule to be within this amount of error like that, to be within 0.0001. Okay, so that's how we get it done with this kind of problem. So now with so much explanation, in the next problem, as I will bring it up, it will be a lot faster because you have seen all of that, and I hope my explanation for the algebra have all cleared it up. So in the next problem, it's still in the same example here, but it's going to be just part B, and we can speed up much more. Okay, and so now, still the same question. We want to find out how large n must be. How large should n be to ensure? Okay, and pretty much the same kind of question, but I call that part B, to ensure the amount of error produced by the trapezoid approximation methods. So ET in absolute value, and actually there is an absolute value here. All I'm saying, I want to ensure ET, the amount of error produced by trapezoid method, is within 0.0001. Okay. All right, so this time instead of EM, we're working with ET. We want ET to be anywhere up and down by 0.0001 from the actual answer. So you can roll back on this video lecture and see my explanation, my logical reasoning earlier. But so ultimately, this statement means we want. Okay, this statement means we want the absolute value of ET right here, of the amount of error produced by the trapezoid method, to be strictly less than 0.0001. That brings in. So the question did not have to bring up absolute value or not, but here we automatically recognize, and my reasoning was given in part A in very much detailed steps like that. Okay, and then now, but on the other hand, we knew that, okay, ET in absolute value has to be less than or equal to a k value times b minus a, all cubed but divided by only 12 n squared. Okay, and that's our error bound formula for ET. Okay, and so in that way, it implies that this expression k times b minus a cube all over 12n squared, it has to be strictly less than 0.0001. And so we would come to that ultimate the result right there. It leads us into this way right here. So it has to be k times b minus a cubed, and over that 12n squared has to be also less than 0.0001. And so all that logical explanation, all logical the reasoning remains exactly the same as how I delivered that back in part A. So that's why part A, somebody might feel it's a little dragging, but because there is so much logical reasoning I would like to deliver there. And now we can start picking up the pace right here. Okay, and so now on my other board, it's exactly the same k. K here has to be a value that satisfied, f double prime in absolute value less than or equal k. Exact same k that we were doing in the error bound for midpoint rule. So in that way, again, I can now make that reasoning that from part A, okay, we can lead to using k equal to 6e. Because it's the exact same k. The two formulas for error bounds, one is the error bound for midpoint rule, but the other one is the error bound for the trapezoid rule, but they both use the same k. And that's why once you found the k from part A, we can reuse that k. So k here is 6 times e right there. And we're still working over the same interval. And again, for this problem, the interval is a is 0 and b is 1. So the interval from 0 to 1 like that. Okay, and so now in that way, that means we are from the previous step, we imply that our inequality becomes 6e times 1 minus 0 cubed, but divided by 12n squared. Okay, and we want that to be less than 0.0001. Okay, and then you can already sense that this step in part B is a lot faster. Okay. And so that means even further that so now we can start doing some cancellation, some famous cancellation work right here. So here I'm looking at 6 can be canceled with 12 and reduce our left hand side to e over 2n squared to be less than 0.0001. Okay, and so now algebraically I'm going to take the reciprocal on both sides of my inequality here that leads to 2n squared over e to be greater than 1 over 0.0001, and that further leads to, so this is a 10,000 again. Okay, so we're looking at 2n squared over e to be greater than 10,000. Okay, to be greater than 10,000. And so that means rearranging the inequality a little further in the attempt to solve for n. So at this point, just like how we've done that in part A earlier, now our goal is to, at this point we have simplified our expression down to only in terms of n dependent on n. And that's the point how we can find out, because we want to find out how big n is. So that's why we're solving for n, to find out that we can reach that requirements being within 0.0001. Okay, so now solving this n right here, I'm looking at n squared to be greater than 10,000, okay, times e, but divided by 2. So one more extra step right here. So n squared has to be greater than whatever comes out from 5,000 times e. Okay, and so now that means n value itself can be found by taking the square root on both sides of our current inequality, and so that gives me square root of 5,000 times e, and allow me another minute or so to do a calculation on my calculator. All right, so the answer right out from the calculator gives me n has to be greater than. So the entire work here, just like how in part A, everything is based on the strict inequality, either less than at start and then switch over to greater than. So here I want n's to be strictly greater than 116.582 and a lot longer. Okay, so that's at start. We want the n is strictly greater than 116.582. But again, n is the number of subintervals, so we desire whole value or integer for n. So that means here we ultimately come to a conclusion, and in that way it has to be at, now in the word of integer, then the least integer that's equal to this, the least integer equal to this, I mean the least integer in this zone right here, in this bound right here, has to be n greater than or equal to 117. Okay, it's not because we round this up, but it's because the next integer value above, the least integer value above that. Okay, and so now that's how big n has to be. Okay, or another way, I don't have enough more space here to write it down, but as a worded final conclusion, n has to be at least anywhere 117, at least 117, and then anywhere above. That should be good. Okay, so that's how we found. So we need 117 or more subintervals in order to achieve that the error produced by the trapezoid method to fall within that. Okay, to fall within 0.0001 of the actual answer right here. Okay, and here we can, the point is we're working completely without worrying about what the true value of I is. We just know that anytime we have an I, and instead of doing the actual I, we're doing an approximation, then there will always be some kind of error. And so the amount of error here can be forced to be within this amount as soon as we meet, as long as we use that many subintervals or more. Okay, so that's the kind of example here in problem 3 right here. All right, so now along in that way, I have already finished talking about error bounds for trapezoid rule and the midpoint rule. So now Simpsons rule that we cover here also has its own error bound here. Okay, so for Simpsons rule, it's going to become a little bit more challenging, but the error okay, so the amount of error produced by the Simpsons rule in absolute value. So ESS right here, or I believe earlier I was using ES. Okay, so the error of the amount of error produced by the Simpsons rule is in absolute value is proven to be less than or equal to, now I used K in the two earlier formulas, so here allow me to use a different constant, even though many textbooks use the same K actually. Okay, but they have to explain K differently. So here I decided to use a different letter so that you have to clearly understand it's not the same constant. It's a constant, but it's different constant. Okay, Q times B minus A to the 5th power and over 180 and to the 4th power. Okay, so the same understanding, quite a few same understanding here, quite a few similar understanding. B is the final point of our integral, our integration interval, and this is the beginning of our integration interval. And then Q is a constant that, so Q has to be a constant that satisfies the 5th derivative, I mean the 4th derivative. Okay, the 4th derivative of the function f. Okay, and again, in absolute value, we want Q to be that constant that satisfies the 4th derivative of the function f in absolute value less than or equal to Q. Okay, so it's all that same argument. So you can think of this Q here as the maximum of this 4th derivative, and to clarify, in the interval from A to B. Okay, and then of course n is the number of subintervals. So this formula is proven. All right, and so now let's get started. Let's use this work right here. Let's use this understanding. And again, all that logical reasoning was made in example 3. So I could have called this next example part C of the example, but I want to keep it as a separate work right here because we have a separate formula. Okay, so we're now calling that example 4. I'm writing it down, but mostly everything stays the same. So here in our example 4, okay, we are given an integral, and the question now, and the only question I'm asking, Okay, and the only question I'm asking is that how large should n be to ensure the estimates using Simpsons rule? Okay, the estimate using the Simpsons rule is to be within 0.0001. Okay, so now I have, we can speed up some process, but then some other process we have to slow it down a little bit, so that just a little bit of a warning ahead of time right here. But so in this, we want the error that produced by the Simpsons method to be within 0.0001. So that means we already knew what we desire. Okay, we want ES in absolute value to be less than 0.0001. That's one thing for sure. Okay, and then, but in the meanwhile, according to the proven formula, then we already knew that ES in absolute value has to be less than or equal Q times B minus A to the 5th power and over 180 n to the 4th. We know that. This is something we know. And so just like how I was explaining that in example 3 part A earlier, we can go ahead and, so combining these two inequalities, then we lead to the following important understanding right here. That means what we want in what we desire, then it leads to Q. This is what we want right here. This line right here is what we want, and combining what we want with what we know right here, it leads to knowing that Q times B minus A to the 5th power over 180 n to the 4th has to be strictly less than 0.0001. That's how I'm seeing it. All right, so now let's move over to the other board. And now this Q must satisfy this requirement. So obviously we need the 4th derivative. Okay? And the reason, now anyone viewing this video see a reason why I stay with the exact same integral, because I don't want you to waste your time reinventing everything. Okay, we already had up to 2nd derivative from example 3 of this problem. So 2nd derivative was, so 2nd derivative of this function was 2 plus 4x squared times e, okay, to the x squared. So we already had that, okay, and you can quickly with your papers and pencil calculate out f prime, f triple prime. So we definitely need f triple prime, okay. So f triple prime here is as far as the calculation, is 12x plus 8x cubed times e to the x squared, okay. And then now so 4th derivative, okay, then this is going to get me 12 plus 48 x squared plus 16 x to the 4th. All right, and then times e to the x squared. That's our that's our 4th derivative as a function of x again. So once you got out of calculus 1 or the differential calculus, then any derivative is generally a function in respect to that main variable right there. Okay, so in that way, now how I'm seeing it, again, allow me, so I want the idea is I want to see this is as maximum, right? So Q, so in the way how I'm seeing Q is the maximum, okay, underline that for me. It's the maximum of absolute value of 4th derivative of the function f, okay, at least in the interval from 0 to 1. That's how I see about this Q right here. Q satisfies this inequality, but that also means Q is the maximum value of this expression, of this 4th derivative of f, okay, in the interval from 0 to 1, at least in that interval from 0 to 1. Generally the interval that we're integrating over, that we're taking the integral over. Okay, so now once we realize the real nature of Q, allow me to explain how I find that maximum, not so calculus one methods, but using the graph, just like how I did that in part B right there. I mean in part A of example 3. Okay, so let me erase this. Just keep in mind we're looking for the maximum of this fourth derivative of f on the interval from 0 to 1. And so if anyone feeling that I'm going a little loose about keep not mentioning about the absolute value, because so now the graph will answer it all clear. All right, so on the browser here, on my Desmos on the computer screen, this is the fourth derivative of our f of x function right there. Okay, so the fourth derivative as a function x, as a function in terms of x. All right, so apparently, and the ending of this graph, you can see that I'm not taking the complete graph of f to the fourth, the fourth derivative of x. But I'm looking at only at the function only inside of the interval from 0 to 1 right here on my x-axis. That's why it only has a short piece, and clearly, and this is making it a lot more clear that this fourth derivative of f of x right here is an increasing function, at least in that interval from 0 to 1. All right, so in very similar argument that I've made in example 3 part A right there, then realizing that our function is increasing from the left to the right, then I can just simply tackle down right there at the right end point. That has to be our maximum, okay, in this interval. Our maximum in this interval of this f to the of this fourth derivative of our f of x function, okay. And so that means now from that graph, here's how I can find Q. And on the graph earlier, you can see that the entire graph is above the x-axis. Okay, the entire piece of graph, at least in that interval from 0 to 1, is above the x-axis. And so having absolute value, being in absolute value or with our absolute value is going to be the same in that interval from 0 to 1. And that's the reason why I can work freely without the absolute value sign right there. Okay, so now I can simply find, by observing the graph, right, we can find out that Q can be found by simply the fourth derivative, which is this expression right here, fourth derivative of f, but substituted in x equals 1. All right, and so now in that way, 12 plus 48 times 1 square plus 16 times 1 to the fourth, all that there, times e to the 1 power to the square power. Okay. And allow me again a minute to do a calculation on my computer screen calculator. All right, so I'm looking at, so my Q value really is 76 E. I decide to keep the whole E right here the same in exact expression. So now I've found Q to be 76 E. All right, and so now I'm going to erase all this space right here to continue our work with that. All right. All right, so now from that expression, from that inequality we have led to up to that point right here, then now that means in the next step, then we're looking at now Q is being 76 E. Now B minus A is going to be 1 minus 0 to the fifth power divided by 180 n to the fourth power. And we want this expression here to be less than 0.0001. Okay, so being less than 0.0001. All right, so lots of cancellation can happen, and especially 1 minus 0 is just 1, and to the fifth power is just 1. So that means I can also do 180. I'm going to start taking the reciprocal 180 n to the fourth divided by 76 E has to be greater than, and again we've seen this many times enough, so 1 over 0.0001 is the same as 10,000. Okay, so we want that expression, the reciprocal of our expression here is to be 180 n to the fourth divided by 76 E. I want that to be greater than 10,000. Okay, and so now that means we can solve for n right here, but the first thing is to rearrange the inequality to achieve n to the fourth has to be greater than, so now I'm looking at 10,000 times 76e and divided by 180. Okay, and then in that way, so I can just straight, at this point the expression is getting a little lengthy, so I'm gonna just dump all of that into a calculation, work on my calculator. So that means n to the fourth, n itself right here, solving for n from this. N has to be greater than the fourth root. It's raised to the fourth power, so here we have to do fourth root. So the fourth root of whatever comes out from 10,000 times 76e and divided all that here by 180. All right, so I am going to again use my calculator for the computation. All right, so the final answer here comes out saying that, so in that way n must be anywhere greater than 10.3504 and a lot longer, of course. Okay, but in the end, again, n has to be a whole value. N has to be a whole value because it's the number of subintervals. Okay, so in that way, with that logical understanding, then n must be anywhere at least. So n greater than or equal, the nearest integer above 10 point something is that 11. So n must be at least 11. So we have to use anywhere 11 subintervals or more to ensure this amount of error produced by the Simpsons method is to be within the 0.0001. All right, so that's how we solve these kind of problems, looking for a desired number of subintervals that reach a certain amount of error produced by any of our specific approximation methods like that. Okay, within a certain amount of error. Okay.